This is 1.5 complex numbers. Before we get into this, and some of this you should remember from a prior class, but just a couple definitions. When you're talking about an imaginary number, that literally is the square root of negative 1. Like when you start taking, you start coming into problems like this, and you take the square root of both sides, and then what do you do when you have a negative inside the square root? So you still have plus or minus, and then it's 2, but then because of the negatives inside, the square root of negative 1 is I. So that's why we put the imaginary number on there. So, and just also as a reminder, there's a correct format, A plus BI. And A plus BI is the correct format. It has a real number component and an imaginary component. So like if I had something like 3 plus 4i, this is the real number, and this is the imaginary number with it. So you literally have two different aspects of it combined together. So even the number 9, just the number 9, this is like 9 plus 0i. So it does have a real number component, and it has 0 imaginary numbers combined with it. So any numbers like that, it can be written in A plus BI format to be able to do that. And that's the basic idea of complex numbers. And so now we're going to start talking about adding and subtracting, multiplying, and even dividing complex numbers. So let's start talking about adding. So here we have, notice this is A plus BI format, and we're taking A plus BI format. And really what we want to do is add like terms. So we're going to combine the real components together. So that's going to be -2. And then we're going to combine the imaginary components of it. So that would be positive 2i. All right, and that's this is my new complex number to be able to do that. Notice it's in A plus BI format. All right, so let's talk about dividing complex numbers here. And notice you can't have a imaginary number on the denominator. Much like when we have a square root of something like that, how we rationalize that, we multiply by square root of 3 times the square root of 3, and the reason for that is on the denominator, square root of 3 times the square root of 3 is a 3, so we want to rationalize the denominator. Well, that's what we want to do here. We don't want irrational numbers on the bottom, but we also don't want imaginary numbers on the bottom as well. And so what we're going to do is we're going to multiply by something that will make it non-imaginary. We want just the real component on there. And what we're going to do is take 2 plus 3i. This is the conjugate, the complex conjugate. And so we're literally going to FOIL this. And let's do the denominator first, just to prove why'd you choose 2 plus 3i? So watch what happens when I use the distributive property. So we got 2 times 2 is 4. 2 plus 3i is 6i. Negative 3i times 2 is negative 6i. Notice the imaginary numbers are going to cross out. And then we have negative 3i times 3i, which is negative 9. I times I is I squared. And remember what I squared is, and we kind of talked about the square root of negative 1, but I squared is also a negative 1. So that right there is a negative 1. So that literally, this right here is going to change to plus 9. And so these cross out, those cross out, and then 4 plus 9 is going to give me 13. Notice there is no imaginary number on the denominator anymore. And then here we're just going to use the distributive property here. So we're going to get 8 plus 12i plus 12i. And then plus 18i squared. And again, I squared is negative 1, so this is literally negative 18. And negative 18 plus 8 is going to give us negative 10. So negative 10 plus 24i. And we always want to try to write it in A plus BI format. So this is negative 10 thirteenths. That's my A. And then I got 24 thirteenths I. So A plus BI. That's the correct format for that. And then just one final comment. If I said something like m equals 2 minus 3i, if I just let m equals that. So then all of a sudden, as far as the notation is concerned, if I do m with a bar over it, that is like the conjugate of that. So this would be 2 plus 3i. So it's possible that I might say something like m times m, again, with a bar over it. And what I want you to do is basically take 2 minus 3i and then multiply that by 2 plus 3i. Okay, so again, you need to be familiar with the correct notation for complex numbers and the conjugate as well. All right, so let's actually solve a problem here. Notice this is a quadratic, so we're going to end up with, rather two numbers, two real numbers, one real number, or imaginary numbers. And we can use the discriminant if we wanted to do this. We could try to factor if it factors. We could do completing the square if we want. But let's start off using the quadratic formula. So we got x equals negative b plus or minus the square root of b squared minus 4ac. And that's all divided by 2a. So once we start plugging this in, so notice I did the first couple steps here. I just plugged it all in. Notice I end up getting a negative number inside the square root, which tells me right off the bat that there is no real solution here. It's going to be some imaginary numbers. And so what we're going to do is simplify this to basically 4i. So we've still got plus or minus 4i. And we're going to literally write this, simplify this. Remember, it has to be a plus bi format. So we're going to have 24 over 8 plus or minus 4i over 8. And that goes to 3 plus or minus 1/2 i. Again, a plus bi format. All right, and that's how you solve that using the quadratic formula. And then just a side comment. Notice that if we wrote them separately, 3 plus 1/2 i, the other one's 3 minus 1/2 i. So they're actually conjugates of each other. So literally, you could see that if I multiplied those together, the middle terms would cross out. So that's just interesting to note with the quadratic.